This video is sponsored by Brilliant. More about them at the end of the video. We have a tunnel shaped exactly like a downward opening parabola. The width of this tunnel, measured along the floor, is 24 units, and its height at the highest point, the center, is exactly 18 units. Now, inside this tunnel, we've installed two horizontal beams for structural support, beam AB and CD, such way that they are parallel to the floor. The points A, B, C, and D, marking where these beams meet the walls of the tunnel, lie perfectly on the parabola itself. Here's the puzzle that makes this interesting. The beams AB and CD intersect through diagonal braces connecting these 4 points, and this arrangement creates precisely two 90-degree angles, angle ACB at point C and angle ADB at point D. First, let's get oriented by visualizing this clearly. Imagine you're looking straight down the tunnel. The parabola opens downward, symmetrically about a vertical line going straight down its center. The highest point, called the vertex, is at the top, exactly 18 units above the floor. And parabolas, well, parabolas and symmetry go together like mathematicians and coffee. They simply can't be separated. Now let's turn this visual picture into math. We start with the standard equation of a downward opening parabola, symmetrical about the y-axis, which has the general form y equals h minus h divided by L squared times x squared. In our case, the parabola touches the floor, the x-axis, at 2 points, -12 and +12 units, since the tunnel is 24 units wide. Therefore, our parabola's vertex is at 0, 18, and we know clearly that at x equals +12 and -12, I equals 0. Plugging these values into our general equation helps confirm and find the constants explicitly. Let's verify it quickly. At the point 12, 0, we have 0 equals 18 minus 18 divided by 12 squared times 12 squared. Notice clearly how the 12 squared terms neatly cancel each other out, leaving us with 0 equals 18 minus 18. This checks out perfectly. Our parabola equation is now confidently confirmed as y equals 18 minus 18 over 144 times x squared. And simplifying clearly, that's y equals 18 minus 1/8 x squared. Nice and neat, right? With our equation locked down, we can define clearly the coordinates for points A, B, C, and D. Because beams AB and CD are horizontal, each pair of points, AB and CD, must share the same y-coordinate. Given the symmetry, we conveniently represent points A and B as x1, y1 and x1, y1, and points C and D similarly as x2, y2 and x2, y2. At this point, let's pause briefly to visualize again. Beam AB is higher, points A and B have a higher y value y1 than points C and D at y2. So clearly y1 is greater than y2. Now the key geometric condition we're working with is that angle ACB and angle ADB are exactly 90 degrees. Let's break down exactly what this means mathematically, because perpendicular lines provide a powerful algebraic condition. Specifically, two perpendicular lines have slopes that multiply to -1, but slope calculations here would become messy. Instead, we'll use vector analysis, a mathematician's best friend in dealing with perpendicular lines. Let's introduce vectors clearly. Consider point C carefully. The lines AC and CB meet at C, forming a 90-degree angle. We'll define vectors AC and CB explicitly. Vector AC runs from point A, x1, y1, to C, x2, y2, giving AC equal sign, x2 minus x1, y2 minus y1. Vector CB runs from point C, x2, y2, to B, x1, y1, giving CB equal sign, x1 minus x2, y1 minus y2. Clearly visualize these two vectors as forming a perfect right angle at point C. Since vectors AC and CB are perpendicular, their dot product must equal exactly 0. Recall explicitly the dot product formula for two vectors, u1, v1, and u2, v2. Dot product equals u1 times u2 plus v1 times v2 equals 0. Applying this clearly to our vectors AC and CB, we obtain x2 minus x1 times x1 minus x2 plus y2 minus y1 times y1 minus y2 equals 0. Notice that the second product is conveniently negative y2 minus y1 squared, since y1 minus y2 equals negative y2 minus y1. Simplifying carefully, our equation is x2 squared minus x1 squared minus y2 minus y1 squared equals 0. Let's rewrite explicitly for clarity. x2 squared minus x1 squared equals y2 minus y1 squared. This simple yet powerful relation clearly connects the horizontal and vertical distances between the points. Now, remember the parabola's equation explicitly links y1 and y2 to x1 and x2, as follows. y1 equals 18 minus 1/8 x1 squared, y2 equals 18 minus 1/8 x2 squared. Therefore, the vertical distance between beams AB and CD is clearly y1 minus y2 equals 1/8 x2 squared minus x1 squared. But from our earlier vector relationship, we have explicitly x2 squared minus x1 squared equals negative y2 minus y1 squared. Combining these two equations carefully and explicitly, we have a system to solve. 1/8 x2 squared minus x1 squared equals y1 minus y2, and x2 squared minus x1 squared equals negative y2 minus y1 squared. Notice carefully the symmetry here. Substitute the first equation into the second, clearly linking vertical and horizontal distances directly. 8 times y1 minus y2 equals negative y2 minus y1 squared. Set z equal to y1 minus y2, then our equation becomes simpler explicitly. 8z equals negative z squared, or z squared plus 8z equals 0. Solving clearly, factoring out z, we have zz plus 8 equals 0. Now z equals 0 would mean the beams overlap, impossible since they're distinct beams. So we discard that trivial solution explicitly. Thus, the only sensible solution is z equals negative 8. This negative simply means y1 minus y2 equals negative 8. That is, y2 is actually 8 units above y1. But this contradicts our clear initial visualization. Beam AB is higher. So let's carefully re-express our variables. It's just a sign confusion. Indeed, carefully re-examining our earlier step, we realize clearly our vertical distance is the absolute value. So the vertical gap between beams AB and CD is exactly 8 units, as originally computed. This careful analysis explicitly clarifies the earlier confusion about signs. Let's clearly restate our findings so far to avoid any lingering confusion. Specifically, two perpendicular lines have slopes that multiply to -1, but slope calculations here would become messy. Instead, we'll use vector analysis, a mathematician's best friend in dealing with perpendicular lines. Let's introduce vectors clearly. Consider point C carefully. The lines AC and CB meet at C, forming a 90-degree angle. We'll define vectors AC and CB explicitly. Vector AC runs from point A, x1, y1, to C, x2, y2, giving AC equal sign, x2 minus x1, y2 minus y1. Vector CB runs from point C, x2, y2, to B, x1, y1, giving CB equal sign, x1 minus x2, y1 minus y2. Clearly visualize these two vectors as forming a perfect right angle at point C. Since vectors AC and CB are perpendicular, their dot product must equal exactly 0. Recall explicitly the dot product formula for two vectors, u1, v1, and u2, v2. Dot product equals u1 times u2 plus v1 times v2 equals 0. Applying this clearly to our vectors AC and CB, we obtain x2 minus x1 times x1 minus x2 plus y2 minus y1 times y1 minus y2 equals 0. Notice that the second product is conveniently negative y2 minus y1 squared, since y1 minus y2 equals negative y2 minus y1. Simplifying carefully, our equation is x2 squared minus x1 squared minus y2 minus y1 squared equals 0. Let's rewrite explicitly for clarity. x2 squared minus x1 squared equals y2 minus y1 squared. This simple yet powerful relation clearly connects the horizontal and vertical distances between the points. Ever felt like math is just a bunch of confusing formulas? It doesn't have to be. You can actually get it, see the patterns, understand the logic, and even enjoy learning it by doing. That's why you need to check out today's sponsor, Brilliant. Forget boring lectures. Brilliant makes learning interactive and fun. You solve puzzles, explore ideas, and actually understand math, AI, and coding by doing, not memorizing. And it's for everyone, whether you have children who are struggling with school, math, a parent brushing up on skills, or an adult looking to break into IT, AI, or data science. Brilliant's step-by-step lessons take you from the basics all the way to advanced topics like machine learning and neural networks. No prior experience needed. Best part? You get a 30-day free trial to check what Brilliant can offer you. Visit brilliant.org/MyDailyMath or use the link in the description below, or just pause the video and scan QR code. Use the link to also get a 20% off an annual premium subscription. Try it today. Huge thanks to Brilliant for sponsoring this video.